So again, last class we started learning about the derivative, which is the slope generator function. We learned about the definition of a derivative, which are these two equations right here, these two limit statements. The one that's blue should give you an equation. The one that's green should give you a number. Gives you the slope at a particular point. These two limit statements require a good amount of algebra to complete. And if you remember, this is questions 1 through 6 on your homework. You have to use the definition of a derivative on 1 through 6. But after that, mathematicians were like, man, there's a lot of algebra. I bet you anything there are some patterns that come around whenever you start doing this. And once you know it, there are patterns, which is what we went over in the basic derivative rules. You have your derivative of constant rule, power rule, constant multiple rule, and sum and difference rule, which you can see here. But the reason that we want to be able to do these slopes, remember, because it's finding slopes, is because it allows me to do instantaneous rate of change at a particular point. Since the derivative is also the expression for the slope of the line tangent to the graph of a function, we can use the derivative to find the slope of the tangent line at a particular point. So this instantaneous rate of change that we've been estimating up until today is actually just the derivative. The instantaneous rate of change is f prime of x for the two definitions of a derivative, specifically when we're looking at a point. But we're not going to be using the definition of a derivative now that we know our derivative rules, because it just saves us so much time if we know what we're doing. So f prime of a, meaning the derivative function with a plugged in, will give you the slope of the tangent line. So that's what we're going to do in example 3. We're going to find the slopes of the tangent lines at the given value of x. In other words, find the instantaneous rate of change at the point given. So for this problem, we're going to use derivative rules to find this derivative problem. So if I were to be looking for f prime of x, which again indicates that I am taking the derivative, we go piece by piece. We have a power rule, a power rule, a power rule, and then a constant. For the power rule, you just take the number up at top and you multiply it in front, which means this first term should derive to 4x cubed. Move the 4 to the front, subtract 1 from the power. What should the derivative of the second term be? Negative 6x squared. Okay, cool. Yes, because the power, there's a number in front of it, so when we move it to the front, you have to multiply it.
Oh, you multiply. Oh, so you multiply it and then you just take away that square.
Correct. Yeah. Negative 2 times 3 is negative 6. 3 minus 1 is 2.
Plus 10.
Plus 10 what? X. To what power technically? 1, but we don't write it because ugh. And then the derivative of negative 8 is 0. Again, I feel it's very satisfying to just cross it out.
Wait, the derivative?
The derivative of any regular number is 0.
Regular? So that includes negative as well?
Just without a variable.
Oh, okay.
So there we go. We have the tangent line. This is what we did last time, is we just found the derivative equation. But we can use this derivative equation to find the slope at a particular point. Since we are asking to find the point or the slope at point negative 2, all that means is that we're going to plug the number negative 2 into this equation. And we've been plugging numbers into equations since forever. You can use your brain or your calculator to do this. Since these are our notes and we're learning, we're going to use our brains, but obviously later in a pinch, you can use a calculator. Negative 3 cubed is negative 3. Negative 2 cubed is negative 2 times negative 2 times negative 2. That's negative 8. 2 times 2 times 2 is 8. Negative times positive, negative times negative is negative. The second equation, negative 2 squared, is positive 4. And then 10 times negative 2 is negative 20. Again, we're just doing this in our brain to practice computation. It's obviously just something you would type in a calculator. Negative 32 minus 24 minus 20 is equal to negative 76. So the slope of that quartic function at the point negative 2 is negative 76. That is a very steep negative line. Its slope would be down 76 over 1. Very steep. But that's the slope. Not something you want to find by hand, because I'm going to lose count if I'm counting 76 spaces down. So instead we use this. Does that make sense how we did that?
Yes.
Okay. Not B. I want you guys to try C. We're not ready for B yet. Go ahead and do the same thing for C. Find me the slope of the line tangent to this graph at x equal to -1. So when we take the derivative here, first of all, we rewrite g prime of x to show that I'm doing the derivative step. This should be 8x cubed minus 9x squared plus 8x plus 2. Did we get that part?
Yes.
Cool. What number or what place on this graph am I actually trying to find the slope of? So we are going to take this number -1 and we're going to plug it into the equation because we want to know at the value -1, what is the slope of the tangent line to the graph? So we're finding g prime of -1, just by plugging in -1 into the equation. That's a brain or a calculator moment. We'll do it in our brain since we're in class and we can practice. -1 times -1 times -1 is -1. -1 times -1, +1. 8 times -1 is -8. Then we have +2. Again, just because I'm doing this in my head, this is -8 minus 9 minus 8 plus 2, which is equal to -23. So the slope of the tangent line to this quartic function at the value -1 is a slope of -23, down 23 over 1, rise over run.
So the derivative is basically y.
If you plug in a value to a derivative, it's actually m, because it's a slope. But it does become a y equals equation. Like it's a whole equation when you get to this part right here, where I haven't switched to the red handwriting yet. That's an equation that's a y equals, technically dy over dx, showing it's a derivative of that function. They're related to each other, so we have to indicate that with our notation. Okay, I skipped b on purpose. We're going to do b together. Those of you who were here last class, before we did a problem like this, before I took the derivative, what did I do?
Oh, you put that on the top.
I was rewriting the equation before I take the derivative. I don't like taking derivative of functions where I can't see the exponent in the numerator. So before I do anything else, I rewrite this to be -3x to the -5 power. Do we see why that happened?
Yes.
Because the x to the 5th was in the denominator, and when it moves to the top, it just simply becomes negative. Now I take the derivative because now it's a cute little power rule. H prime of x, indicating that I'm starting to take the derivative, is going to be what?
-3 of, no, it's -15. +15 of 4.
It is -6.
You're subtracting one.
Oh,
-5 minus 1 is more negative, -6. Okay. Those of you who were here last time, did I let you leave your answers like this?
No.
No, when we cleaned it up, how did we write our answers?
Yes.
Put it back. This is going to be 15 over what? X to the 6th. Okay, much cuter that way. We like. That's the derivative. But we are doing derivatives in this problem to find actual slopes at particular points. What point am I trying to find the slope of? So at the value h prime of -1, that just means plug in -1 to the equation. What's -1 to the 6th power? Is it positive or negative?
I'm guessing it's positive.
Even powers makes it positive, yes. So it's positive. What's 15 divided by 1? Ah, that is the slope of the line, or the curve, that rational function there, at the value -1. Has a slope of up 15 over 1. It's a slope.
So how did we get from 15x raised or -6 to 15 of x over 6?
We just cleaned up. We technically don't leave answers with negative exponents, especially when they asked you the question with positive exponents. It would be like answering in kilometers for a question somebody asked you in miles. Like it's the same. It's yes, but that's rude. Give them back the answer that the way they asked it.
So like, what if they changed the whole question though? Or you just got rid of the...
Nope. Nope, it's an equal question. They're the same thing. One is written with positive exponent, one is written with negative exponent. They're equal. So the reason that we want to do this, where we find the slopes, is because it actually allows us to do really interesting things with our calculus. Once we find the slope of the tangent line, we can write entire equations for lines that are tangent to it. The way we're going to do that is we're going to throw it all the way back to Algebra 1. When you used what was called point slope form. Ooh. Can you reach back in your brain and find out where point slope form is in your brain? Oh, great. Good start. Y minus y1 equals m x minus x1. In point slope form, listen to the name point slope form. What two things do you need to write it? A point and a slope. Those are things we can find using calculus because we just spent 3 problems finding slopes, right? And we're going to be given part of the point where we can find the other part. So in these problems that ask you to write an equation, not just find the slope, but write an equation of the tangent line, you need 2 things, and we'll find them one at a time. First thing we need is we find the point, because we have to have a point. I already know part of the point. It's right there. Which part of this coordinate point did I already find? X. How do you find y's when you know x's? Plug them in. Great. We're going to take this equation, f of x, but we're going to plug the number 2 into it. So 3 times 2 cubed minus 2 times 2 squared plus 4 times 2 minus 2. Notice I did not plug that into the derivative. I plugged it into the actual function. After lunch, we'll finish this problem. So if you remember before we went to lunch, we were working on finding the point, which we also remembered just meant that we have to plug the x value into the function to get a number out. Because we're in class, we'll practice doing this in our head. 2 to the 3rd power is 8.
You were asking us, are you saying something about why we didn't plug it into the derivative? Is it because we're looking for y plus?
Correct, yes. So the derivative function is going to give you the slope, so we'll get there. That's how we're going to find the slope. But when you just want to find the point, you just plug it into the regular equation, not the derivative. 3 times 8 is 24. 2 times 4 is 8. Plus 8 minus 2. To do this fast in our head, the 8s are going to cancel, so it's really 24 minus 2. That means the slope, or the point, is 22. Now this is important because now it gives me the coordinate point that I'm going to be plugging into point slope form. What is that coordinate? Something comma something. 2 comma 22. We have an x value, we have a y value. Awesome. We have the point. Because this is called point slope, what do we need next? Find the slope. But we just learned how to find slope from an equation. We take the derivative, we plug the number in. So if we look back up at the original equation, what is the derivative of f of x?
2.
Nope. Start at the beginning.
Oh. X. 0. Oh. Wait, where?
9. There we go. 9. X to what power? Squared. And then what?
Oh.
Negative 4. X.
Plus 4.
Just plus 4. Very good. Now, that's the equation of the derivative. That's going to be my slope generator. It generates slopes when you plug stuff in. What number are we plugging in?
2.
2. So we're finding f prime of 2, which would be my slope at that point. This is 9 times 2 squared minus 4 times 2 plus 4. Obviously, at this point, it's just computation. Use your brain or your calculator. This is 9 times 4, bless you, minus 8 plus 4. I'm just showing an aggressive amount of work here. I know you would probably plug that into a calculator, but this is 36 minus 8 plus 4, which is 32. And now we can put it in point slope. Because we have an m, we have an x1, and we have a y1, that's all we needed to plug it into that equation that y'all told me at the very beginning. So the equation of the line tangent to the graph at the given point would be y minus 22 equal to 32 times x minus 2. Now I know you are generally uncomfortable leaving answers like this because we drilled it into an Algebra 1 that you write it in y equals mx plus b form. You don't have to. It said write an equation. That's an equation. If it said write the equation in slope-intercept form, yes, you would have to distribute and move, but it just says write an equation. Don't do extra work that's going to cause you to make a silly math mistake. It's an equation. Call it done. Yes? Can we practice this one on part B? And by we, I mean you. Great. I'm going to leave this example showing, and I'll give you some time to write the equation of the tangent line to the given point for this graph. I'm going to start writing because at this point we either know what we're doing or we're stuck. Don't look until you're done if you know what you're doing. Yeah.
I don't know if I wrote the answers to the first question.
Yeah. The final answer?
Yeah. So, oh, you just put it like you would the formula up here, right?
1000% yes.
Thank you.
That's crazy. I've never heard of that.
But what if they don't live that? Yeah, but what if they can't celebrate their birthday because they're gonna live leap year?
What are we worrying about? Are we worrying about math?
So we
Yes.
use the math.
We always up there.
Well, technically, yeah, because if you're born on the 28th of February, you can't really celebrate your birthday for like 4 years.
We're discussing the statistics of birthdays.
Wait, it's 28 years. Those,
Okay.
Miss, I was so confused how you got -12 until I realized I plugged in a 2 for the derivative.
-12.
Oh, oop. No, -12 is right.
Something wrong.
Wait, what?
It's like 120 for some reason.
So here's what we should have done for this one.
Yeah.
What would you be?
We first found the inputs and outputs. Input is given to us. Okay, we plug that number in, we get y. This is x, this is y. Hooray. Then you take the derivative and plug in the value you care about to get the slope at that point. You get -12, then you just plug everything in. How do we feel about that?
Pretty good.
Okay, so the rest of the class is going to be some time for you to work because between all the people who were gone last time who need to kind of review what we did last time and the fact that I gave you a lot of homework, we need some practice time in class. I will say I need everybody to look at the homework. The few of you who picked up your homework from me ahead of time, I forgot to print the answer key on the back until afterwards. So if you want to grab a different copy that has the answer key, that would be great. Also, everybody needs to change the instructions on the third part. My bad. It says find the instantaneous rate of change for each function at the given x value. Fine. Then find the equation of the line tangent to the graph of each function at the given x value. Fine. It says write the equation in slope-intercept form. Don't worry about it. Just write it in point-slope form, just like we did in the notes. So don't worry about it being in slope-intercept form. Just write it in point-slope form today. So the answer key also does that, just point-slope form.
So no slope-intercept form.
No slope-intercept form unless you want to flex and do that as well, but you don't have to.
Why is there 7?